Hello, so this lesson is a nice quick review of some computing probabilities. This is good for our PreCalc class. It's also a good review for Algebra 2 students or anybody getting ready for the SAT test. So welcome to all our new friends. We have to review some vocabulary. So basic probability is generally written as a fraction, sometimes a decimal. But there's two main types that we're going to talk about, theoretical versus experimental. That's the first thing we're going to talk about. And theoretical is what should happen. So like if you're rolling a dice or flipping a coin, if the law of probability is true and it's a fair dice and coin, we think we know what should happen. How many times should it roll a 6? How many times should the coin flip tails versus heads? But experimental is what happens when you actually go through and run trials. So that's the big difference, is running trials versus just thinking what it should come out to. And then later on in the probability and statistics problems, we start to look at, is this unusual? Are these results unusual, or are they okay, or can we accept them? And obviously it gets more complicated. So this question we're going to have to save for class because we have to do a little count of, how many girls and boys are in the class. But deck of cards, that's not different. So standard deck of playing cards, remember we have 52 playing cards total. And of those 52 cards, there's 4 suits. I would draw them for you if I could. But we have diamonds. We have spades. Oops. We have clubs. And we have hearts. So remember that diamonds and hearts are red. And then spades and clubs are black cards. And then within each suit, those are called suits, we have 13 cards, 2 through ace, or ace through king, however you want to denote the ace. Whenever I say something like a face card, they're referring to things with faces. So king, queen, and jack would be our face cards. And we're not going to argue over whether ace is high or low, because that could depend on the game, so that's not going to be notation that I need you to think about. So if I write this notation, it says, what's the probability of choosing a red card? So if I just reach into a deck of cards without looking, the probability of choosing a red card, well, 26 of them out of the 52 are red, which of course we're going to reduce that fraction to 1 over 2. Half the deck is red. So for a heart, there are 13 of each suit, so 13 out of 52, which reduces to 1/4, which makes sense because heart is one of the 4 suits. Now as far as red 7s go, there's a 7 of diamonds and hearts. So there's 2 red 7s in our deck, and that fraction is going to reduce to 1 over 26. I like reduced fractions for answers, mostly because I don't have to grab a calculator, generally. But I've seen a lot of college textbooks where they want everything as a decimal, so whatever. And then this is kind of a trick question, black heart. You aren't going to find a black heart in the deck of cards because their hearts are red, so there's 0% probability that is going to happen. Oh, there's a good graphic for you. My bad. So that's way better than anything I could draw. There's our deck of cards. Okay? Oh, there's another one. Okay, here we go. So if I'm rolling a 6-sided dice, the sample space is what could happen. So you could roll a 1, or a 2, or a 3, or a 4, or a 5, or a 6. So sometimes it helps to draw out your sample space. The probability of rolling a 4, well, that's 1 out of the 6 outcomes. So that's a 1 out of 6. Even number would be this guy, and this guy. So that would be 3 out of the 6, which of course we're going to reduce to 1/2. Now be careful here, probability of number greater than 1. Don't include 1 in that count, so it would be 2, 3, 4, 5, 6. So 5 out of our 6 numbers. And then you're not going to roll a 7 on a 6-sided die, so there is a 0 probability of that occurring. I love those trick questions, huh? Bill, John, Sue, and Ann are all up for a promotion, and their boss is going to choose a team of 2 people to lead the department as a promotion. Everyone's equally likely. What are the possible teams that we could come up with? So it could be Bill and John, right? It could be Bill and Sue. It could be Bill and Ann. Or, now when I go to select with John, I'm not going to say John and Bill because that's the same team here. So we'll say John and Sue is another option. John and Ann. Again, moving on to the next person, Sue. She already has been paired up with John and Bill in these outcomes, so it's just Sue and Ann. So we have 1, 2, 3, 4, 5, 6 different teams we can create. So what's the probability that Bill and Sue are the team that's promoted? Well, that was 1 out of our 6 teams. the probability that the team is made up of 2 men. This is the only team that has 2 men, assuming that Bill and John are men and Sue and Ann are women. So that would be 1 out of the 6 again. And then the probability that Ann is at least one of the people getting the promotion. So here's Ann, here's Ann, here's Ann. So that would be 3 out of the 6 teams. So Ann has a 50% chance of being on a promotion. Actually, all of them have a 50% chance. So that's nice. All right, this question. I hate this question. So we have to figure out what are the possible outcomes of a couple having 4 children. Okay. Birth order constitutes a different outcome. Ready? I'll start with my nightmare. 4 boys. Closely followed by my second nightmare. 4 girls. Frankly, 4 kids. That seems like a nightmare to me. Now, what if I go back to the all-boys pairings and we have 1 girl in the mix? Okay? That's the opposite of my family. We have 3 girls and 1 boy. My childhood family. So what if that 1 girl is the first child born? So girl, boy, boy, boy. And then what if I just move where she's located in birth order, one thing at a time? Let's do this systematically. Boy, girl, boy, boy. And what if she's third in the birth order? Boy, boy, girl, boy. And boy, 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 girl at the end. Oh my gosh, can you imagine being a baby girl with 4 older brothers? That'd be awful. Alright, so what if there's 2 girls and 2 boys? This one always trips me up because I always forget one of them, so hopefully I'm better today. So what if it goes boy, boy, girl, girl? What if it's boy, girl, boy, girl? What if it's boy, girl, girl, boy? What if it's girl, boy, boy, girl? And what if it's girl, boy? Girl, boy? Did I get that? Okay, and then I feel like I didn't get girl, girl, boy, boy yet. Did I? Nah. Girl, girl, boy, boy. No. I know there's supposed to be 16 outcomes when we're done, so I'm keeping that in my brain. So we did 3 boys, 1 girl, 2, 2. Now let's do 3 girls and 1 boy. That's not my family. So, what if it was a older brother? Girl, girl, girl. Or this is how my family works. Girl, boy, girl, girl. How about girl, girl, boy, girl? And then a baby brother with 3 older sisters. Yikes, that might be the worst than having 4 older brothers. I don't know. Alright, I have 1, 2, 3, 4, 16 total. Very good, we got them all. Yay, yes. 16 total possible outcomes. Yeesh. Alright, what's the probability that you do have the nightmare of all 4 girls? Well, that's only 1 out of the 16 things we wrote down. All boys, 1 out of 16. And then this question, at least 1 boy. You can go through and count up how many combinations here have at least 1 boy, but this is the only one that doesn't have, no, back up, not that one, this one. This is the only one that doesn't have at least 1 boy. So 1 out of the 16 don't qualify for this, so that means 15 out of the 16 are going to have at least 1 boy in the family. So really high probability that you'll have at least 1 boy if you have 4 kids. So dads and moms of the world who are really hoping for a son, I guess you just keep having kids, right? I have 2, that's enough. Alright, probability rules, so some notational things. This is the notation they use for probability of an event, A. Excuse me. Probability is going to have to be some number between 0 and 1, because it either is not going to happen, or it will definitely happen, or something in between there. And the closer to 1, the more likely the event is. If you have a sample space, all their probabilities should add up to 1 or 100%. But that would be assuming you have all of the sample space, right? And then the probability of something not occurring is 1 minus the probability that it occurs. So like, this is called a complement. So this is a good example here. If the probability of an event occurring is 3 out of 5, what's the probability that the event will not occur? Well, the way I think of it is I say 3 out of 5 times it will occur, so 2 out of 5 times it's not going to occur. But if you want to use the formula they just gave you, 1 minus 3/5, common denominators and all that, right? 5/5 minus 3/5 is how they get the 2/5 mathematically. For our class, typically the questions are going to have context to them, so they're going to make a lot of sense. But in college, I've noticed they give a lot of questions that have no context, and they just say, like, probability of event A is this, and you don't have any context with it, so you don't really know what it's talking about. So you really have to understand the formulas. All right, when you have compound events, more than one event, the idea is you're supposed to multiply the probabilities together, but it gets a little complicated when your events are not independent or they're conditional. So at first, let's talk about just simple independent events. You just multiply them together. So rolling a dice and flipping a coin, totally independent from one another. What's the probability that you're going to roll a 5? Well, that would be 1 out of 6 on a dice. And then flipping a tail on a coin would be 1 out of 2. And if we multiply those together, you got 1 out of 12. I'm so sorry. So this time we're rolling a pair of dice, and while they are the same thing, they're 2 different dice. So the probability that you're going to roll a pair of 3s, 1 out of 6 chance on the first dice, 1 out of 6 chance on the second dice. So not a great probability, but 1 out of 36 that you're going to roll a pair of 3s. This question is very depressing. So you have test A and test B, and you have a 40% chance of passing test A. So that tells me we have a 60% chance of failing test A. I should write that in red. Fail. Unless we want to fail it. I don't know. Maybe it's one of those. And then I can't see the rest of this problem, but it says the chance of you passing test B. Come on. There we go. Oh, 20%. Yikes. Not good. So the chance of failing test B is 80%. 80%. That's not good. Alright, so these tests are independent of each other. So what's the probability that we're going to fail A and B? Well, that would be the 60% multiplied by the 80%. We have a 48% chance that we're going to fail both tests. Yeesh. Alright, fail A would be 0.6, but we're going to pass B. That's good. 0.2. That is not a good chance. 0.2, or 1.2, so 12%. Pass A would be 0.4 multiplied by failing B, which is 0.8. It's a 32% chance. Yeesh, not good. And, let's dream about passing both tests. So 0.4 and 0.2 is 0.08. You have an 8% chance of passing both tests. I hope these are the kind of tests we want to fail. Now, if you were to add all 4 of these together, because this is the entire sample space, right? These are the only outcomes that we can have. They add up to 1 or 100%. So that's a good thing to notate. We do a lot of that in stats class. So what if our events are dependent? Now, there's this really funky little formula, probability of A times the probability of B, that given that A has occurred. And there's even more formulas than this, but I think if you just think about the question, it's so much easier to compute. So let's assume we know all about the deck of cards again. What's the probability that you pull 2 aces in a row and we don't replace them? So the first time I reach into the deck, and the probability of me pulling out an ace, there are 4 aces in the deck, right? So 4 out of 52. So I get an ace, I set it to the side. Now I go to reach in again. The probability of getting another ace, well, there's only 3 left in the deck, and there's only 51 cards in the deck now. So if I multiply these 2 probabilities together, which I already did, so I'm just going to steal my answer, it's a 1 out of 221 chance. Not good. And that was assuming we just had a single deck of cards. Alright. I'm always impressed by poker players who can do the probability calculations, because they're not even as simple as that. Because they have multiple decks that they're working on, and they have to keep track of that. Ugh, couldn't even imagine. Alright, in our class we have 17 boys and 13 girls, so 30 total students. We're going to select a president and vice president. What's the probability that we select 2 females for those roles? So the first time they go to choose a president, the probability of that person being female is 13 out of the 30 students. Well, whoever I just selected is out of the running. So there's 1 less female, and there's also 1 less total student in the class that I can choose from for vice president. So 12 over 29 would be the next fraction, and I already multiplied these together on my key, so that's 26 out of 145 when I reduce that fraction. Lovely. So, see, we didn't really use a formula, we just kind of thought really hard, right? But the word or is a tricky one in math, because or indicates that there's multiple things that can happen and still be constituted as a winner, if you want to think of it that way. So the probability of A or B occurring would be the probability of A plus B, but then you have to subtract the probability of A and B occurring, Because you've counted this twice. It's the old idea of a Venn diagram. If you think about the overlap as them both occurring at the same time, right? If I were to add up everything in this circle plus this circle, I've counted this overlap twice in my calculation. So I have to take it away one time to counterbalance the fact that I added it twice into my formula. However, there are events out there where they don't occur at the same time. They're not possible, and that vocab is called mutually exclusive events. So I'm pulling from a deck of cards the probability of pulling a red card or a 2. So I'm going to show you the formula, and then I'm going to show you how I think about it, and you decide what makes you happier. So if I think about pulling a red card, that would be 26 out of 52. Pulling a 2 would be, let's see, there are 4 2s, right, because of every suit. But we double counted red 2s twice. So there's a 2 of hearts and a 2 of diamonds. So I have to subtract those off because I counted them twice. So that's how you come up with, I think I did this one already. Oh, 7/13 is how it reduces. Now for me, what I do is I say, okay, there's 26 red cards. And then if I think about all the 2s in the deck, I got 2 of each suit, but I've already counted the 2 red ones. So I just add the 2 I haven't counted in yet. So I get 28 out of 52, which is the same fraction. So it's up to you, however you want to think about it. I feel like this formula, if I have context, I don't really need it, because I am doing the subtracting myself, but it's up to you. Now we're rolling a dice, and the probability of us rolling a 3 or a 6. Well, if you're rolling once, you can't roll both a 3 and a 6. It doesn't work that way. So these are what we call mutually exclusive, there we go, exclusive events. So you don't have to worry about subtracting anything. So there's 1 6 on the dice, there's 1 3 on the dice, so that's a 2 out of 6 probability. There's nothing to subtract. So you have a third chance of that happening. And then 6 or even, now that is not mutually exclusive because there's 1 6 on the dice. But then even numbers would be 2, 4, 6. So there's 3 of them technically. However, you've counted the 6 twice, haven't you? So you got to subtract that off. Now for me, I don't do the problem that way. I say, okay, here's my sample space. 6, winner. Anything even, winner. 3 out of 6, half, answer half. That's how I do it. It's up to you though. Alright, let's keep going here. Math class is 14 seniors, 8 juniors, 5 seniors are male. Okay, so let's talk about these seniors. There's 5 male, which means there must be 9 female to add up to 14. And then for our juniors, there's 4 and 4. So sorry. So senior or male. You can use that OR formula where you subtract, right? You could take all the seniors and then add in all the males that you see. So 5 and 4 is 9. But you've counted these senior males twice. So you have to take them away one time in the formula. Or, this is how I would have done it. There's 14 seniors. And then any other males out there that I haven't counted, these 4 males. So that's how I'm going to get 18 out of 22, which, yep, I should be able to do that in my head. I know, 9 out of 11, right? Yeah. So same idea for a junior or female. You can use the compound of the union formula, or you could say, right, there's 8 juniors, but there's these 9 females I haven't counted yet from the senior class. So that's 17 out of 22. And then junior or senior, those are mutually exclusive. So I would just say 14 plus 8 is 22 out of 22. And that's a 100% probability. Alright, this gets fun, right? Your doctor is going over all the stats of a risky operation. Yeesh, depressing again, 25% failure rate. So that means we have a 75% success rate. Silver lining and all that, right? Now, even if your surgery works, you still have a 17% chance of infection. But on the flip side of that, that means we have an 83% chance of no infection if your surgery works. So 83%, okay. Your surgery can fail, you still get infection. 3%, okay. Oh, geez, that's depressing. What's the chance of you having a successful and infection-free surgery? So these are dependent events, so you have to kind of make sure you pull the right formula. So 75% chance that it's successful, and then once you know you're successful, you still have a 70% chance of infection, but we said that's an 83% chance of being okay. So I'm going to have to multiply these together, which I didn't do. So whatever that is. All right, a clothing store. This is more my alley because this happens to me all the time. You have a 30% chance of the pants being too tight. So that means a 70% chance of being okay. Oh no, back up. 10% chance of being loose. Huh. What's the probability that the pants actually fit you? Well, I'm going to kind of group these together and say there's a 40% chance that they just don't fit. So the complement to that, 1 minus 40%, 100 minus 40% would be a 60% chance that they do fit. There we go. So, yeah, am I using formulas all the time? No, because I don't need to. I just don't. To meet state standards, Harlem does some research and discovers 80% of the students need help with math, and 70% students say they need help with English. But then there's an overlap, like that Venn diagram. 55% of the students say, I need help with both math and English. So that would mean we're going to add up our probabilities of math and English, but then we have to subtract off this overlap because we counted these kids twice. We counted them here and here. So I'm going to cheat because I already did this. It comes out to a 95% chance probability that some student that you select is going to need some tutoring with math or English. These are my favorite. These are called contingency tables, and it's a way to organize conditional probability. So the first two questions are just basic. It says, what's the probability that you choose somebody who's an independent? So there are, 9 independents out of the total 17 independents out of the total 140. And I don't have a calculator right now, so I'm not going to be reducing these for the sake of time. Sorry. Production worker, here we go. 92 out of the 140. Independent or production worker. Okay, well, we could take these two numbers we just found, the 17 plus the 92, but we counted these dudes twice. We counted the independent production workers in both of these numbers. So we're going to have to subtract that 8 out of 140, so I think it comes out to 101 out of 140. Okay, this is cool. So it says, probability that you're going to choose an executive given that your person is a Republican. So that tells me I'm only allowed to look at the Republican data. So zone in on that. Within that data, there are 34 executives out of 55 total. That is what conditional probability looks like. There is a really nasty formula for it, but in all my years of teaching this, that's the best way I can come up with. I think that's the easiest for kids to understand. And then here, independent, given that you're a production worker. So this time, you're only allowed to look at data from the production worker row. So independent would be these 8 dudes out of the total 92 production workers, which I think I did reduce that to 2 out of 23 for you. So whenever the word given, or they might, instead of the word given, they'll put like a big line like this, that means given in statistics. Just to be weird, they gotta have notation for everything, right? Okay, counting trees. Oh gosh. Okay. Trees are awful. So I'm going to do one, and then I'm not going to do another one ever again. So flipping a coin and then rolling a dice. So I flip a coin. It's either going to land on heads or tails. But then after that, I'm going to roll a dice. So 1, 2, 3, 4, 5, 6 outcomes. And you guessed them. There are 1, 2, 3, 4, 5, 6. And then you're supposed to follow the tree branches. So like one outcome is heads 1, heads 2, heads 3, heads 4. They're useful, just, I don't know, probably not as much for us as I would like. So let's talk about what's called the fundamental counting principle. I have 30 students, everyone can only hold a position, and I want to figure out how many options and outcomes there are. You can just multiply them together. So when I go to choose a president, I can choose from all 30 kids, but I already selected a president, so the next time I can only choose from 29, and then the next time only 28. So when I multiply those together, I get 24,000. 360 outcomes are possible. Pretty cool, huh? I'm not doing this problem again. I refuse. I'm the teacher, I can do that. All right, so permutations versus combinations. Permutation is where order matters, is the way we say it in math. What it means is if I rearrange the order, I get a different outcome. So if you see words like order, arrange, assign, place, like placing things in a line, line up, I see that one a lot too. Those are all words that indicate we're looking at a permutation. A combination, you're going to see words like team or committee, group. Group's kind of a weak one. There's other words, and you just have to kind of think of, this is the way I think of it. If I were to rearrange two people in my selection, does that give me a different outcome, or is it the same outcome? So if I flip the order of which I always tell the kids this example. So I'm going to choose 5 of you to go to Disney World with me. Does it matter what order you're selected in? No, you just want to be chosen. So that's a combination. But if I say, I'm going to choose 5 of you to go to Disney World with me, and the first 2 people I choose are going to fly on the airplane, and the other 3 people are going to have to take a Greyhound bus down to Disney. Well, that makes a big difference, right? So the order in which you're chosen is going to make a difference, therefore we have a permutation, set of permutations there. So here, 32 people in our class, we're choosing a team of 3 people, so that is a combination. So this is how we're going to write it down on our paper. 32 combinations, choosing 3 people. The total comes first, how many you're selecting comes next. And then we go to our calculator, because there is a formula, but I'm going to show you the way we're going to cheat. And you type 32, math, and then go over to probability, and down to NCR. That's the combination choice, so 3. 32 combinations of 3. 4,960 is our answer. That's how many ways you can select a team of 3 people out of that class. Wow. Oops. All right. For the sake of time, I'm not going to flip back and forth with my calculator. So just remember, guys, you're going to the math menu and over to probability once you start typing. 8 students are being placed in a line. That is a permutation, because when I arrange the order of just one or 2 people, it gives me a different arrangement. So 8 people, and we're choosing all 8 of them to line up. So type in 8, go to math, probability 8, and you get 40,320. Let's spend a day doing that, right? No, that'd be dumb. Waste of our time. All right, this question always gets kids because they can't believe how big this answer is. We're going to choose a committee of 4 boys and 4 girls out of the 20 boys and 50 girls. So what's happening here is we have a combination because of the word committee. We have 2 different combinations. So for the boys, I have 20 boys, and I'm choosing a committee of 4. And then for the girls, I have 15 girls, and I'm also choosing a committee of 4. And then you're going to multiply those together. I suggest you practice this one on your calculator. If you do it in one step, you have to get out of the first combination before you do the second combination. So that's my warning to you. It's huge. It's 6613425. Yikes. No, that's not the right place for a comma. 6,613,000. Oh my gosh. That's a lot of committees you can create. And then here I'm arranging, so that's a permutation. 5 videos and 7 DVDs. So I'm arranging them together as a group, so I have 2 different permutations I'm multiplying together. So 5 permutations of 5 is being multiplied by 7 permutations of 7. And again, huge number, right? 604, 800. You could spend your whole afternoon arranging all your DVDs and videos. And all you kids out there are going, what's a video? All right, we're going to end the lesson there. That is a review of a whole lot of probability stuff, and we need to practice the heck out of it. So good luck.